Hello everybody, this is a screencast on the subject of descriptive and analytical statistical tools, which will be of use to you as you write your internal assessment for biology. Of course, this is in the time of COVID-19. I do hope that watching this screencast many times and winding forward and back to the relevant sections to you will mean that you're able to include some high quality statistics in your work. So let's get started. We're going to begin with something called descriptive statistical tools. Now some of these you've heard of, I'm sure. The mean, symbol x bar, the standard deviation, symbol lowercase s, the standard error, sometimes called standard error of the mean, which has that symbol there, and we have our confidence intervals, the 95% level. Why do we calculate all of these values? It's ultimately so that we can plot error bars on a graph. So when you plot your mean values on the graph, whether it's a line graph or whether it's a bar chart, the cross or the top of the bar represents the mean value that you're plotting. Around that mean value, you're expected to include error bars, which can be rather large or rather small. And this value here, 95% confidence interval, allows you to plot appropriate error bars for your data. So we're going to consider a worked example. And that worked example is actually in keeping with the theme of COVID-19. I've chosen a date here, a few days ago, and I've chosen 5 European countries and 5 Asian countries. Ultimately, what we're going to try and do here is plot a bar chart with countries down here, number of new cases on the 7th of September here, and I'm sure that you can appreciate, even by looking at the data, we're going to have 2 bars, one of which, probably for Asia, will be higher. But the point here is I'd like to show you how to calculate these error bars based on the data I've just shown you. So how do you calculate the mean? Well, that's easy. I'm sure that you don't need me to tell you that. But just to show you the formula, it's here. N is the sample size, which is 5, because we're calculating 2 means. We have 5 European countries and 5 Asian countries. So, of course, what you do is you add all those together and divide by 5. There's your mean. Add all those together, divide by 5. There's your mean. The standard deviation is a little harder to calculate, and if you're doing it manually, or if you're doing it using a spreadsheet and typing in the formulae, be very careful. Make sure you're adding together the appropriate values. So, if we have a look at the data in front of us, we can see that the standard deviation for Europe is smaller than that it is for Asia. And that would make sense just looking at the data here. The spread of data around the mean, or the range, is much smaller in Europe than it is in those Asian countries. That means that the value for standard deviation for Asia is going to be larger. But again, look, it's the same expressions we've seen already. This could be new to you. So we're now at the 3rd row in the table I showed earlier. The standard error could be a new expression for you, but don't panic. It's actually easier to calculate than the standard deviation. Standard error is the standard deviation divided by root of the sample size. So it's simply a case of getting your standard deviation number and then dividing that by the square root of 5 in both cases, and that's what we find for those 2 groups of countries. The standard error can then be used to calculate the 95% confidence interval values. There it is, look. So how do we do this? Well, the first thing to say is that there are actually 2 values for 95% confidence interval. There's a lower value and an upper value. More on that in a moment. So how do we find this? Well, it's the mean value, which we calculated earlier, plus or minus 2 times the standard error. So let's do my mathematics. Here we go. So what we do is for, let's say, Europe, the mean is 399.4, so that's the mean, we have to initially add 2 times the standard error, which is 61.11. That will give us one of our values for 95% confidence interval in the case of Europe. The other value would be simply changing that plus to a minus, and the same expression applies. So 2 times 61.11, because that's the standard error. You can do that, I'm sure, and I'm sure you can do that on your own for the Asian countries, and if you carry that calculation through, what you'll eventually find is you'll find that you get these values here. Okay. Now, they have names. These 95% confidence interval values have names. They are the upper and the lower limits. So this is the upper limit for Europe, this is the upper limit for Asia, that's the lower limit for Europe, that's the lower limit for Asia. Again, you're probably thinking, well, where am I going with this data? That's about to be revealed to you, but that now is the end of our calculations for descriptive statistics. Not too bad, I hope. Where next? Well, try and take a photographic image in your mind of those 4 figures. They're going to be very important in the next slide. Okay, so remember those mean values? Well, we've now plotted them on a bar chart. So 399.4 is the mean value of Europe, and 1567.6 is the mean value of Asia. So, and don't forget, I'm sure you know this, that the top of the bar is the mean. That value there represents 5 values. Okay, that value there represents 5 values, and the top of the bar is where we plot them. Easy stuff. So where do our 95% confidence intervals come in? Well, this allows us to plot these 2 error bars. And again, I've done this pretty roughly. There's no scale on the y-axis, but that's not a problem. I'm going to label it up for you. So again, those 4 figures are very important. Let's see why. Here is the European error bar. And of course, if you were doing this on graph paper, what you'd have to do is be very careful, and you'd have to plot this error bar such that the top part of the bar extends to the upper 95% confidence interval. And then, of course, the lower part of the bar extends down to the lower 95% confidence interval. Same thing with the Asian countries. You can see these 2 figures here dictate where we draw our error bar there. What do these error bars tell us? Well, specifically, the 95% confidence interval represents the range of the sample data, that's our sample countries, in which the true value of the population mean lies. Now let's just make this specific to our example. What that means is that we only took a sample of 5 European countries, and we only took a sample of 5 Asian countries. There are many more European countries than 5, and there are many more Asian countries than just 5. So what this error bar tells us, let's just look at, let's say, the European one. It tells us that we have a 95% confidence, or rather a 0.95 probability, that the actual mean for European countries, all of them, not just those 5, lies within that range. Okay? I'll say it again for the Asian countries, because that's quite challenging to get your head around. So the mean of those 5 was there, but we only looked at 5. And if you're applying this to a lab-based project, you'd be talking about how you only took 5 replicates or 5 repeats. So because we only took 5, we're not overly confident about where the real mean lies. And particularly in relation to Asia, we've got a broad range of data. Our data is not reliable. More on that later. But back to the point, the actual mean value of all Asian countries is said to lie within that broad range there, and we can say that with 95% confidence or a probability of 0.95. of course, that is suggesting that there is a probability of 0.05 or 5% confidence that it lies outside of that range. But statistics is all about probability, chance, likelihood, and so on. We can never be absolutely sure of anything in this world. The other thing that confidence intervals and the error bars you can plot from them allows you to do is spot overlap. Now, we don't have overlap here between the lower confidence interval of the Asian countries and the upper confidence interval of the European countries. There's no overlap there, which suggests that there is likely to be a significant difference between the two continents. But we can't absolutely say that. We have to do something called a statistical test to confirm that that difference between the two countries is significant, scientific, believable, and not down to sheer chance. More on that later. Let's say the Asian countries' error bar extended to here. Now, of course, then you'd get an overlap, wouldn't you? If there's an overlap between error bars, then it's likely that there is no significant difference between those two mean values. Everything I've said so far in terms of plotting 95% confidence interval error bars can be applied to a line graph as well. Clearly, you're going to have to probably do quite a few more calculations. How many do we have here? 1, 2, 3, 4, 5, 6 data points. 6 mean values represented by the 6 crosses. You're going to have to do 6 calculations of 95% confidence intervals, but if you are good with a spreadsheet, you can just plug the numbers in and then copy them through. Let's have a quick look at overlap in this situation. We'll look at this mean value here. And sorry about the fact that the error bars seem to have been shifted to the left a bit. I'm sure you know this, but they should go directly through the cross, yeah? The point is that mean value that I have circled there is likely to be very reliable because the error bar is very narrow. That tells us that the standard error for the mean is narrow or small, and the data was highly consistent. The data was very similar. The data we used to calculate the mean was of a similar size. Compare that with this mean value here, or rather that mean value there. The error bar I've just circled is huge, and in fact the error bar for that mean overlaps with the error bars for 2 other means. Yeah, you can see an overlap going on. What does that say? Well, that suggests that we can't be sure that the difference between those 3 crosses is likely to be statistically significant. Again, we'd have to conduct some sort of statistical test. More on that later. But comparison with this one here, where there's no overlap with any of those 3 here, we're likely to be able to suggest that there is a significant difference between that mean and any of those 3 means. Okay, so that is the end of descriptive statistical tools. We're now going to move on to analytical statistical tools for your IA. And we're only going to look at 2 today. These 2, the student's t-test and the Pearson's linear correlation coefficient, are used for normally distributed data sets. What that means is slightly complicated and don't worry about. However, if I approach you with the bad news to say you can't use either of these because your data is not normally distributed, then we'll have to look at one of these tests. These are not included in the screencast, but don't worry, I'll approach you individually if that applies to you. So the vast majority of us will be looking at one of these 2. What's the point of doing analytical stats? Well, it allows us to decide whether we should accept or reject something called a null hypothesis. What does that mean? Well, a null hypothesis, ignore the alternate one for a moment, is a statement which essentially says to other scientists, look, I'm going into this investigation with no bias. I'm going into this investigation expecting there to be no significant difference between my two factors, or no significant difference between these two continents. So we have to make this statement, which a lot of students query because they think, well, what's the point in stating this? Because I can see that I've got a correlation or a significant difference. It's all about protocol, and in the wide world of science, showing that you are not biased going into the investigation. So the null hypothesis, the key word is no, and you, I'm sure, can relate this to your own study. There is no significant difference between the mean number of new COVID cases on this day in Europe and Asia. Again, you would only use the t-test if you're looking at differences between means, but again, more on that later. If you state a null hypothesis, you should also state the opposite, which is sometimes called the positive hypothesis, because it doesn't include the word no. It's the opposite, it's the mirror image of the null. And later you'll see that if we reject the null, we accept this one. But if we accept the null, we have to reject that one. Okay, straightforward stuff, and almost too simple to get your head around. A lot of people think it's more complicated than that, but it's not. Two statements, completely opposite. Which one is your experiment going to prove? So we're going to look at a worked example again for our student's t-test. There's an interesting story behind why it's called student. I'll let you work that out and research that on your own. But the worked example considers the same data. Okay, and again, we are looking at the student's t-test because we want to see if there is a significant difference, that's the key word, between two mean values, or whether the difference that we have just established in our bar chart between these two countries or groups of countries could be down to sheer chance and a chance event. That's entirely possible. And again, science is all about not proving anything. You can't actually prove anything in this world. It's getting as close to proof as possible. This is a scary equation, or formula, should I say. It's not as scary as it perhaps initially appears. We've seen a lot of these expressions before. X bar, standard deviation, sample size. We know that n is 5. The x bars we've calculated and the s's we've calculated. So it's simply a case of just putting the data into this formula. Okay, so let's have a look. Let's have a closer look at what's going on here. Well, like I said, we've actually got this data ready and waiting for us, don't we? We calculated this earlier on. So the mean values are x bar and x bar 1 and x bar 2. It doesn't actually matter which way you put them round, but I'm going to assume that the Asia relates to 1 and Europe relates to 2. So the European mean will be x bar 2, the Asian mean will be x bar 1, the European standard deviation will be x bar 2, S2. You can tell maths isn't great for me. And standard deviation once is going to be the Asian countries, yeah? I've just made that sound far more complicated than it is, but you can work that out, I'm sure. Plug all those numbers in, and let's try that together. So t equals 1567.6 minus 399.4 divided by square root of all the following, 881.22 squared divided by 5 plus 136.66. It's not a good number, is it? Divided by square divided by 5. And eventually, if you do all that calculation, as I did earlier, you'll find that t is 2.93. 2.93 is the value of what we call our t statistic. And that's very useful. You'll see why now. This is a table of what they call critical values for t, and you can screenshot this and use this in your report, no problem. Some poor individual, or groups of individuals, once upon a time, sat down and worked all these out, and it goes way beyond 30, which is suggested on the PowerPoint. These numbers relate to what they call critical values, which are thresholds above and below which we can make certain decisions. The key point here is we have to calculate something else before we go any further, and that's called degrees of freedom. Degrees of freedom, symbol V, who knows why, for the t-test can be calculated using this expression. N1 and N2 are the same in our case. We've got 5 countries in both continents. So it's basically 5 plus 5 minus 2. So therefore, V for our study is 8. So we go back to the table and we find the row for 8. And just for your convenience, I've extracted it and put it here. This is the row for 8 here. But if you look at the bottom of the table, there's also 2 other very useful rows, and I've copied those across. The first one is the probability that chance could have produced this value of the t statistic, and the second one is a confidence level. And you'll see that they are essentially the same thing, it's just that this one is probability and that one is percentage chance, I guess. Okay, this is where to really concentrate, everybody. Our value of t, whoops, not sure what that is, t is 2.93. And we have to ask ourselves some questions now. Use the following acronym to help you. ALARM. And this all relates to the null hypothesis that I showed you earlier. Let me remind you that was that there is no significant difference between the mean values of these groups of countries. ALARM stands for accept if less and reject if more. Okay, so accept the null hypothesis if the value of t is less than the critical value, and reject the null hypothesis if the value of t is more than the critical value. Okay, here we go. This is the big moment. So let's have a look at our table here. So we've got a critical value of 1.86 in this first column. Now what does that mean? That means that we have to exceed that in order to make a decision, or fall beneath it to make a decision, at this level here. More on that in a moment. Let's just see how t 2.93 compares with 1.86. So 2.93 is clearly more than 1.86. So what does this acronym tell us to do? It tells us to reject the null hypothesis if this value of t is more than the critical value. What's our null hypothesis? Our null hypothesis is that there is no difference. So what does that mean? It means that there is a significant difference. We can accept the alternate hypothesis. Hope you're following. You might want to rewind that and play that again. Now, we can reject the null hypothesis at the 10% level, or with a probability of 0.1, that the results that we saw are down to chance alone. I'll say that again in a different way. We can confidently say that there is a significant difference between our mean values, but only to the point that we admit that there is a probability of 0.1 that chance alone could have resulted in those two means differing to the extent we saw. Whew. This is taking all of my early morning brain power to explain. Okay, that's good, okay? It means that our results show a significant difference and we're 90% sure about it, basically. Let's go to the next column. 2.31, how does that compare with 2.93? Well, 2.93 is again more than that, isn't it? Yeah? So we can now revise our statement and say that we are even more confident that the difference is significant. And we can do that because the data in the table tells us that there is only a probability of 0.05 that the difference in those means was down to a chance event, or down to chance alone. So this is getting better and better. However, you can see what's coming on the horizon, can't you? 3.36. This now exceeds, this is more than our t value. But I shouldn't have said that because it will confuse you. We have to talk about the t-value as the focus. So the t-value is less than, this is less than that. What does the acronym ALARM tell us to do? We have to accept the null hypothesis if our t-value is less. Okay? And what does our null hypothesis say? It says there's no significant difference. So sadly, we cannot say at the 1% confidence level, we cannot say with a probability of around or less than 0.01 that our results are significant in terms of their difference. So the likelihood here is that the probability of those results, those mean results differing, and that being due to a real scientific reason and underlying basis, is somewhere between 0.01 and 0.05 in terms of probability level. Okay, it's a real challenge to express this, and I'm sure you'll find that when you write it up in your IA. Okay, so you might be sitting there thinking, well, I haven't actually got means to compare. Mine's more about a correlation. You know, I've got a line graph and I've got 5 or 6 different means. I've got lots of different means. You know, do I compare each one of those with each other and do lots of t-tests? Well, the answer is possibly. More on that later. But what you'll initially want to do is you'll want to do something called a Pearson's linear correlation coefficient. Now that is very similar in terms of the approach to do with probability we saw a minute ago, but the equation itself, the formula itself, is hideously more difficult to work with manually. And I'll tell you, there's a good website you can use to do this automatically for you, and I'll tell you about that later. But let's go slowly. And the reason we use this rather than the t-test, and around half of you will be using this, and around half of you will be using the t-test, and some of you will be using both. In this case, we're looking for correlation. And you might remember that I showed a similar slide earlier where the underlined word was difference. The only different word here is correlation. So we're wondering now whether there is a significant correlation between two different factors, or whether that correlation is due to a chance events. Just a reminder, a correlation is a phenomenon whereby if one factor increases, then the other reciprocates in some way. The other either increases or decreases. So the change in one factor has an effect on the other. Okay, there's a real cause going on. We hope, although it's not necessarily proven from this. Correlation certainly you'll be familiar with. It's graphs that look like this, it's graphs that look like that. That would be a positive correlation, that would be a negative. Let's go. So I've had to adjust the data a little in order to make it applicable for a Pearson's calculation. So I did a bit of research and I found out that the population of the countries here differs from 6 million in Denmark total to over 250 million in Indonesia. The new cases on that day, I think we've seen already today, are shown there. And if you plot these on a graph, you'll see that there is what I think a fairly strong positive correlation. A line of best fit here would probably look something like that, wouldn't it? But we have to do some maths. And how can we then calculate the Pearson's linear correlation coefficient for this data? How can we prove, or at least get close to proving, that as the population number goes up, the number of new cases inevitably goes up? Let's have a look. Firstly, as usual, before you do any stats, you have to make 2 statements. Again, the word no is key. There is no significant correlation between the mean number of new COVID cases on that day and the population number of a country. And this is the opposite statement. And again, it's all about avoiding bias. I'm not even going to attempt to do this, to be quite honest with you. I tried yesterday and I got completely lost. There are calculators that allow you to do it online. You just plug in the numbers. If you're better at maths than me, maybe you won't trip over the same problems I encountered. But ultimately, I can tell you that the value of R for this data is 0.98. Okay, take my word for it. 0.98 is our value of R for the data you've just seen. We can immediately make a judgment on that data. R, which is called the Pearson's coefficient, will only ever be between -1 and +1. It will never be less than -1, it will never be more than +1. So if your calculation gives you a figure which is beyond those limits, then you've gone wrong somewhere. If it's -1, then you have a perfect negative correlation. So as one factor increases, the other decreases in perfect proportion. And the opposite is true for +1. As one goes up, the other goes up. As one goes down, the other goes down. If it's 0, I'm afraid you've got no correlation whatsoever, which is unlikely. The majority of us will have correlations which are described as weak and strong. Yeah, R1, of course, was up here, 0.98. That's a very, very, very strong positive correlation, which is not surprising because we could almost see that from the graph itself. But this is all, you know, it's semi-quantitative, it's sort of judgment-based. How do we get a bit more objective with our maths? Well, that's where a table like this comes back into play. I'm pleased to say this is a little easier than the one I showed you earlier. For a start, this only has probabilities, but of course you can multiply all these figures by 100 if you want to get chance levels, or confidence levels, should I say. So this one will be 1%, that one will be 10%, of course. Now, we don't have to do any degrees of freedom calculations for this table, which is good news. We just have to look at the number of pairs of data. Well, how many countries was in that previous table? 5. Yeah, we had from Denmark to Indonesia, there was 5 countries. So this is going to be our row here, and everything else we ignore. Okay, so just scrub that out of your brain, all this stuff. Those 4 figures are the only ones we need to be concerned about. Okay, let's go through the acronym again. Here we go. Accept if less and reject if more. So our value of R was 0.98, which is huge. And as you can see, that's more than all of those numbers on the board, okay? Which means that we can reject the null hypothesis because our value of R is more than the critical values in the table. It's probably more than if we were to go down to the 0.001 level, which is not shown. But what we can say is that because 0.98 exceeds 0.874, we can reject the null hypothesis and conclude that the alternate hypothesis is true, i.e. there is a correlation between the two factors. And we can say that with 1%. Sorry, we can say that with the knowledge that the likelihood of that correlation existing due to chance has a probability of 0.01 or less. Okay, it's hard to explain that. And when you show me your drafts, I'll see if you've done it well. But the point is, everybody, 0.98 exceeds every value in that table. You've got a very strong correlation on your hands. And you can see that, like I said, you can see that as one goes up, the other is absolutely going up. Okay, now, I've added a couple or 3 other countries to the mix now, just to illustrate a different story. Spain, Germany and Japan, they don't fit this pattern. Okay, so here's Spain, here's Japan, and I think that's Germany. Okay, they don't fit the pattern. What does that do to our R value? Well, I can tell you that it changes it to 0.65. Okay, so if we did this with extra data, the R value changes, which is not surprising because look, what's the correlation here? Well, the line of best fit is probably there, but some big outliers going on. So again, 0.65, still kind of over here, still a strong positive correlation, but it's not as strong as our previous group of countries. Where does 0.65 end up? Well, don't forget, we've just added 3 countries, haven't we? So we're going to have to look at the 8 pairs of data now. 0.65, R equals 0.65. How does that compare with those 4 numbers? Well, it's more than that one. So that tells us that we are 10% confident we have a significant correlation. It's more than that one, which tells us that we have a 5% confidence level that our data is significantly correlated. But it's less than this one here, okay? As you can see, 0.65 is less than 0.716. That tells us that we cannot say with 2% confidence that our data has a significant correlation. Put it another way, it means that there is a 0.02 or less probability that that correlation is simply down to chance alone, which is less secure than our statement from earlier. So that is a different story, and I'm sure that many of you will have correlations that are very weak. There's no problem with that. Like, you're not going to lose any marks for having a weak correlation or even no correlation. But identifying that correlation as weak and strong, and then finding your Pearson's value and talking about that value in relation to probability is where you get the marks. Like I said, happily, there is a website out there, this is a good one, there's many, which allows you to just plug in numbers to calculators. So here are the t-test calculator and the Pearson's calculator. Give them a go. One final thing is that you probably, some of you, could do all 3 types of statistic that I've talked about today. So you could make sure that you have 95% confidence interval error bars, as shown. You could then do a Pearson's test to find an R value for this correlation here. But then some of you might also want to do a t-test for chosen means. So you might remember that I said this mean here looks like it could be significantly different from that mean there because there's no overlap. Yeah. So a good thing to do might be to actually do a t-test on those 2 mean values. I'll leave that in your capable hands, but that would be wonderful to have 3 different types of stats in an IA report. You could also do a t-test on that one and that one and show the examiner that you have accounted for the fact that the overlap results in an insignificant difference in the data. So this is a bit of a bolt-on to the presentation. It's not really stats at all, but I thought, given I've got your attention, I'll just spend 5 minutes taking you through these 3 terms, which students usually confuse and use wrongly interchangeably. Accuracy, reliability, and validity. So stats are finished. Okay, this is meant to be a more relaxing 5 minutes at the end. What do these 3 terms mean? Well, many of you have seen this analogy before, but I will show it to you again because it's really good and it hopefully will lodge these 3 terms and more in your mind before you start writing about your data. So here's a competition where 5 archers have stood 20 metres away from a target, and their aim is to hit the yellow, of course, the bullseye. In this investigation or analogy, you have to assume that hitting the yellow bullseye is the equivalent to obtaining the actual or true value for a piece of data in a scientific investigation. And it's worth me saying that again because it's important you understand that science can never, ever, no matter what we do, find the actual value of anything. We don't have equipment that measures accurately enough, precisely enough. If you were to measure your height, you'd be limited by the markings on the meter ruler, wouldn't you? So every time you aim to get every time you aim to get that value, the actual value, you're only making an estimate. Okay? Which archer had the most precise technique? Well, this is not so much about the analogy. We need to talk about what precision means. Precision relates to the equipment you use. So if you used a measuring cylinder which has a smaller volume, that's probably going to be more precise than a measuring cylinder which has a greater volume, because the markings on the side will be in smaller intervals. Yeah. Precise equipment and precise methods result in accurate data. I prefer that way of thinking about it. So use the word precision for the equipment and for the method, and then reserve the word accurate for data. So the results here were most accurate for Archer C, because all 5 arrows, all 5 attempts at reading something, if we're relating this to a lab-based pursuit, actually got the real actual value. Yeah, they were very close to reading the actual value. That means they have precise technique, they have a precise method, they're using precise equipment, the bow in this case, or maybe a measuring cylinder in our case, and their accurate data results. Which 2 archers obtain the most reliable results? Well, reliability relates to repeatability, replication of the study, and so on. If you took 5 readings of somebody's height and they were all the same, maybe give or take a millimetre, then your data is very reliable. But if you took 5 height readings and one was 2 centimetres off the next and the final one was 10 centimetres out, then that data is not reliable. It's not consistent, and as a result your error bars are going to be quite wide. The answer here is, well, there's 2 archers, B and C. C has accurate data, we've established, but they've also got very reliable data because it's consistent. The data points are very, very similar to each other. The mean value is going to be reliable. B also has reliable data. It's less accurate. It's not hitting the true value, but the point is it is nonetheless quite consistent. All the data points that student has taken are very similar to each other. Okay, this relates to validity. So Archer A was cheating. They stood 1 metre closer to the target than the other 4 archers. This would invalidate any comparison. What do I mean by that? Well, it means that you can't actually, well, you'd have to cancel the competition, wouldn't you? Or exclude and disqualify Archer A, because you've introduced here a second variable. The only variable that you should be including in this investigation is the archer. But this archer here has stood closer to the target. So we've actually got a confounding variable, or a second independent variable, that is changing, which means that we have an invalid investigation on our hands. That's basically what that paragraph says. Please read it in your own time, but ultimately you need to make sure that all other variables are standardised, and I know that you've done that. So if you were looking at the effect of different concentrations of something on an enzyme, then temperature of that reaction vessel would need to be kept the same for all treatments. You know this, but try and use the word valid if you talk about it. Which score shows a random error? Now that's a new term, and I'd like you to talk about random errors. Random errors cause outliers or anomalous data results. Okay, anomalous data points. This looks like a random error to me. Basically, they've got 4 data points here that are very similar, but there's a 5th that is way out. And you can imagine how this would look in a scientific table of data results, can't you? You'd have 1 data point that was just very different to the other 4. What do you do in this scenario? You would have to ideally exclude that random error, provided you could identify it as one, and then probably take another reading in its place. Yeah, there is always a chance that random error is the true value, and the other 4 are random errors, but it's less likely, and it's all about chance in science. And finally, which 2 archers have scores that show a systematic error? Now, systematic errors relate to the equipment or the method that you're using, and often they can't be identified. It's a real problem in science, systematic error. In this case, it's B and D. How do we know that they are systematic errors rather than random? Well, they get, both of them, reliable results. They're continuously hitting the target in the same kind of area, whether that's in the same literal area or in the black circle. So it's difficult for the scientist to identify this as an error, of course. That's half the problem. You just have to acknowledge that that is a possibility, but that your precision in your investigation in terms of the equipment and the technique was as well designed as possible. So I tend to think of A, R and V in relation to these 3 points, and keep this in your mind, please, as you begin writing and continue writing. A relates to actual. So accurate data is close to the actual scientific value. Reliability relates to R. This means that your data is replicable or repeatable. Every one of your repeats has a similar value. And V relates to validity. And this is the point about variables that I mentioned earlier. Standardizing other variables means that your investigation is valid. Okay, and I believe, on that note, we find the end of the presentation. Thank you for listening.